So we are trying to explore this strange location where this g naught naught term goes to 0, right, at r equals 2gm over c squared. We're trying to figure out whether there's something strange going on there. And so our next task will be to consider motion, radial motion, an object basically falling in towards that location, and then we'll see if anything strange is going on. So we'll sort of see how much time it takes. So if we do c squared d tau squared, right, we're dealing with, so I'm writing the line element, g naught naught dt squared plus g11 dr squared. These are the two terms that we derived. They look a little strange. And then we have the other terms, r squared d theta squared plus r squared sine squared theta d phi squared. And we want this to be 0 and this to be 0. We're not moving around this spherical object, and we're not moving in the polar direction. And we want to get a sense of the time that passes as you're moving inwards, the proper time d tau. So it looks like we're going to be considering this part, but we'll have dt and d tau and dr and d tau. So we need some more information about the relationship between this and that on this specific path. So of course, we know how to do this kind of thing. If we have a Lagrangian, we can get the equations of motion. And so Lagrangian is, it's a kinetic energy minus the potential energy. And so an invariant quantity here that we can easily construct is G A B. This thing is a c squared, so we can do an mc squared kind of thing if we divide by the tau squared. So we have the invariant, the GAB dxa dxb, but we divide that by d tau. And so that looks like this is a good Lagrangian for for getting the equations of motion of this particle in this in space-time such that there are no forces acting on the particle. There's only kinetic energy. So, of course, we need the Euler equations, d by d tau. So with respect to proper time, we have dl by dx dot a minus dl by dxa. That's going to be equal to 0. And so it boils down to some calculations. Let's first write this out. M over 2 g naught naught dx0 d tau squared plus g11 dx1 d tau squared plus, let's just write them all out. These will not matter. What does this look like? It's m over 2 minus c squared, 1 minus 2gm over c squared r, dt by d tau squared, plus 1 minus 2gm over c squared r to the minus 1 dr by d tau squared plus where am I here? G22 r squared d theta by d tau squared plus r squared sine squared phi of d phi d tau squared. So we could either ignore this or sort of set some value such that, actually this is sine squared theta. We could just not have to deal with this at all if we think of theta being pi over 2, right? We could choose any theta, and it's completely general because it's spherical symmetry. But let's consider the A equals 0 in the Euler-Lagrange equations. So in that case, we have d by d tau of dl by dt by d tau, and that is minus c squared, 1 minus 2 gm over c squared r dt by d tau, right? It's this term. And we have dl, we're looking at this, dl by dt, and it doesn't depend on t, so that's 0. So we end up having minus c squared times 1 minus 2 gm over c squared r dt times d tau is equal to some constant. Let's call it a. Okay, so we have a constant of the motion, which can be useful to us. So of course we have the metric, so minus c squared. If we divide by d tau squared, as we were thinking at the beginning, we have minus c squared gab dxa d tau dxb d tau. This is minus c squared equals minus c squared times 1 minus 2 gm over c squared r dt by d tau squared plus 1 minus 2 gm over c squared r to the minus 1 dr by d tau squared. And we have just said we're just putting that equal to 0. We're considering just radial infall, so we have no other term there. And so for radial infall, we have minus c squared is equal to, given the constant of the motion that we just derived, this is equal to minus a squared times or c squared r to the minus 1, right? That's what this term becomes, plus 1 minus 2 gm over c squared r to the minus 1 dr by d tau. And so we see that squared, and so we see that we have our we can get the rate at which proper time varies along the path, the radial path r, right? We got rid of this term using the constant of the motion. So let's rearrange. This gives us dr by d tau squared is equal to a squared minus c squared times 1 minus 2 gm over c squared r. And as we said before, we actually want to integrate over time as we go from some value of r to r equals 2 gm over c squared and see what that looks like. So we want to rearrange in terms of the tau. So we want to flip this, and so we're going to flip this, and so basically we get d tau, and we'll take the square root to isolate the d tau, integrate that. This looks like just too much pressure. Can't seem to learn the amount of pressure. This is over the square root of a squared minus c squared times 1 minus 2 gm over c squared r. It looks like that. And so when we integrate to get the proper time, we're considering doing this integral from some value of the radial coordinate capital R, say, to 2gm over c squared. So I'm just rewriting square root. And the point here is to notice that at this value, this disappears, and we just have a 1 over a term. And when we are at this value, we have a 1 over a squared minus some number, square root. This is a little bit less than this, and so this is greater, this whole thing is greater than this. And so, but the point is, it's always a finite quantity. So we have finite, the range of values over which we're integrating. We could actually consider the integral, but the point is, we always have finite quantities. So there doesn't seem to be anything strange going on. We get a finite proper time in falling from some radial coordinate r down to this radial coordinate. And so it looks like we need to take this location seriously.